What's so special about H2O, about water? Well, water is weird. Among the unusual and important properties of water, which you've begun to study, surface tension. Water is the only substance on Earth that exists simultaneously in all three physical states of matter. If you take an ice cube and set it on a plate or something, then immediately begins to melt, and the water that comes off has a vapor pressure. Water has a very high boiling and melting point for such a small molecule. Its mass is 18 and its boiling point is 100 degrees. Methanol has a boiling point much lower than that, and yet it's nearly twice as dense in terms of grams per mole. The density of liquid water is greater than the density of ice. That means that ice will float on water. Usually, when a liquid substance, freezes, little small particles form, and the solid is denser than the liquid, and so it kind of rains little particles down to the bottom of the test tube. Water is not like that, and water is very polar. Metabolites, especially your proteins and carbohydrates, and of course ions, sodium, potassium, and calcium, and so forth, are soluble in water because of the polarity. Lipids, however, are not soluble in water. If we look at the boiling points of the hydrides of group 16, that's where oxygen is, we see hydrogen telluride here a little below 0 Celsius, hydrogen selenide down around -50, hydrogen sulfide even lower. And if we were to predict where hydrogen oxide would be, it should be down here nearly -100 degrees Celsius. But in fact, water boils at plus 100 degrees Celsius. That is certainly an anomaly. If we look at the group 17, hydrogen iodide, hydrogen bromide, hydrogen chloride also decline. Hydrogen fluoride is much higher. It's actually a liquid a little bit above 0 degrees at 1 atmosphere pressure. We see the same kind of thing happening in the nitrogen group, group 15. We have antimony, arsenic, phosphorus, and ammonia. Then the boiling point jumps up. But we don't see that in group 14, the carbon group. It declines pretty regularly. That's almost a straight line. So something's kind of special about oxygen, fluorine, and nitrogen. When you did the surface tension investigation, the so-called penny lab, we saw, or we can see with the alcohols that are analogous to water, propanol, ethanol, methanol, the surface tension, as we measure in terms of drops, should go down. And it does for propanol, ethanol, and methanol. When we get to water, the surface tension jumps way up. If we measure, and we can look this up on the internet or the handbook, if we measure the heat it takes to vaporize a mole of these alcohols, and we start with the butanol, then propanol, ethanol, methanol, that enthalpy of vaporization goes down pretty regularly here. It's almost a straight line. And then we would expect that when we take the CH3 group off and are left with only H2O, that the enthalpy of vaporization would be down here around 35 or 36. But in fact, it's up here almost at 41. It has an enthalpy of vaporization almost as high as that of propanol, which is way, way larger in the late 60s. And of course, water's molar mass is 18. And then, of course, we can do a lab right in our own laboratory showing the boiling point of in this case 4, 3, 2, and 1 carbon alcohols, and we can see that the boiling points decline very regularly until we get to water. We take the CH3 group off and are left with only H2O, and we have a boiling point at 100 degrees at 1 atmosphere pressure. Water then is anomalous. It doesn't fit the patterns. By every measure, the intermolecular forces between water molecules are way higher than we would expect if we compare that to analogous compounds. You see this whether comparing the hydrides of group 16 or the homologous series of alcohols, of which water is the trivial case. It's the alcohol without any carbon. Why is this? In comparing water with the other group 16 hydrides, we see that something about oxygen is way higher than any of the others. And that's, of course, is Pauling electronegativity. As you go from polonium to sulfur, and you can see a fairly regular increase as we go from the larger to the smaller, the Pauling electronegativity does go up. But when we get to oxygen, it just leaps up. Where it has been below 2.5, it leaps up to almost 3.5. The oxygen in the OH group attracts the 2 electrons in the oxygen-hydrogen bond very, very strongly, a lot stronger than any other of those group 16 elements. In fact, the electrons are so attached to the oxygen atom that the hydrogen is slightly acidic. We know that if we throw sodium into water, it'll actually react with the water and give off hydrogen gas, just like it will with any acid. But the alcohols all have OH groups too. In fact, if you take methanol and put sodium in it, it will react and form hydrogen gas, although very, very slowly. The other alcohols will do the same. So it's something is going on beyond the high electronegativity of oxygen, or maybe working with that high electronegativity, that magnifies the effect and makes water far more attractive to other water molecules in the intermolecular attraction. And what is it? Well, Dr. Pauling postulated that just as the light electron pairs in a covalent bond, as you can see here with this animation, they're being shared by 2 atoms, and those light electron pairs being shared by 2 atoms will reduce the total energy and increase the stability of the interatomic linkage. So the light hydrogen atom in water, which is attracted to its own oxygen over here, it's also attracted to the adjacent oxygen in the next molecule, might also increase the stability, that is, reduce the total energy in the intermolecular linkage. Now, this is not what the hydrogen bond looks like. It's just an animation I'm providing showing how the bond, since it is an attraction to the 2 molecules, can reduce the total energy of the system. So the hydrogen bond has been symbolized in this fashion as an attraction, mutual attraction of the hydrogen atom in one molecule to the oxygen of an adjacent molecule. And that reduces the total energy by about 20 kilojoules per mole. So it's not as strong as a covalent bond between the hydrogen and the oxygen here. It is much weaker than that, maybe even almost about half the strength. But as you can see, it does reduce the total energy. The typical strength of a water-to-water hydrogen bond is negative 20 kilojoules per mole. You can see here the difference in the distance in the covalent bond is about 0.1 nanometers, and in the hydrogen bond is 0.177 nanometers. Hydrogen bonds, of course, between the nitrogen bases in the DNA molecule hold the 2 DNA strands together. It's important that they be held together, clearly, in the nucleus, but it's also important that they be allowed to, use the word, unzip. and the enzymes that unzip them so that they can form the matching RNA molecule, those enzymes don't need to use a whole lot of energy. It would be a very bad waste of energy to use a whole lot of ATP in order to break these bonds, because they're just going to reform after the molecule makes the RNA. So that should be a very low energy. That is the difference. Hydrogen bonding also holds proteins together in muscles and enzymes. And you can see here examples of how that happens. This alpha helix is held together, you can see, by hydrogen bonds between nitrogen, hydrogen, oxygen here. These amino acid residues are very far from each other here, and yet they bend around so that they can form the proper shape. And it's the shape of a protein, of course, that enables it to be an enzyme and catalyze chemical reactions in the cell. Also, the various beta sheets here are held together by hydrogen bonds, here between nitrogen, hydrogen, oxygen, and that's typically how that goes, nitrogen, hydrogen, oxygen, or in this case carbon, oxygen, and the hydrogen that is attracted to this nitrogen here. So that's hydrogen bonding that holds the proteins together. They're also, again, weak hydrogen bonds, so these proteins can't stand a lot of heat or that'll break the hydrogen bond. That's what happens when you heat an egg and you see the egg white start to congeal. What you're doing is breaking hydrogen bonds as you cook the egg, and that's why when all of those cross linkages get broken and then they reattach, you can't see through the egg white anymore. Hydrogen bonds also force the water lattice to open up close to the freezing point and increase the volume as water is turning to a solid. And as you can see here, when you dissolve an ionic solid, the positive ion is attracted to the negative end of the water molecule, and the negative ion, the anion, is attracted to the positive end of the water molecule. So when they solvate, S-O-L-V-A-T-E, you have a different orientation of the water molecules around the two kinds of ions. One last thing, detergents and soaps mix nonpolar molecules with water, and you can see here the sodium dodecyl sulfate here, which is a detergent, is an amphipathetic molecule because it brings water and grease together. The sodium end is attracted to the oxygen end of water, and the big aliphatic sulfate you see here, that end mixes easily with the nonpolar fat, oil, or grease, and so you can scrub the grease off your hands with soap or detergents like this. So what's so special about water? High electronegativity of the central oxygen atom, second only to fluorine. High polarity of the water molecule, and of course, hydrogen bonding.